Um, I am an architect and we are based out of Pune. We have a studio in Pune, about 35, 40 architects. We work on a diverse range of projects and some of them, all our projects are quite interesting and some of them have a little different to do. Like we've sort of started experimenting with steel a lot in the last decade or so. So as I normally say with people who both come to visit our projects and to interact with us, that with concrete, you can do poetry. It's a beautiful material. You can mold it the way you want. With steel, you can do symphony. It's a different set of elements that come together, that connect and create a vibrant structure. So that is what I'm going to show you today. A few of our structures and how it is. The other advantage is that we deal with a few structural designers and we've sort of never compromised on both our aesthetics, on the dream, as well as the detailing. So the detailing of concrete is one of the elements that we are going to look at. So this is a project that we've done for Forbes Marshall. We've been working with them for the last 15 years. This is a factory done in Chakan, completely in steel. It's designed by Mr. Bal Kulkarni, is also here. So this structure is basically different spans of different sizes. The height is about 13 meters. The column is something which didn't sort of come up overnight. We worked about 6 months trying to figure out the column, which would both composite, it would take cranes, it would have MEP in between, it would have supports. If you see, there is no cross support. The support is only in one direction. So this is the skeleton and when completed, how it is. So the idea is both it's lightweight, it was fast in construction, plus it's aesthetic, and plus it's a green, sustainable structure. This is how the space was from inside. So it's got spans ranging from 18 meters to 27 meters across, and about 6 meters in the shorter direction. The height goes up to 13 meters. This entire workshop is about 100 meters deep, completely naturally lit. Ventilation was, the idea was to have it naturally ventilated and exhausted until the government said, no, you need evaporative cooling, and then these duct socks were introduced much later after the building was designed and erected. So when we started designing it, so we started as architects sort of experimenting in what the column should be. These were the various studies we'd done for columns. It's not that we sort of came up with an option and okay, this was A and this is the solution. Our structural designer would come and say it doesn't work, or it fails miserably, or it's over-designed, it's under-designed, and then we would go back to the drawing board and start again. So it was an experiment, it was a learning process, and we sort of learned how to adapt to this material, how to learn this, live with this material, and how to mold it into the way we want. These are various options done from various types when, okay, changes would come from the client side and how they wanted the elements to work through, how the crane, the loading of the crane would suddenly change, how the truss would sort of sit on top. So all these details were done. It's only that after our study and our research, we sort of came up to a structure that would be something like this. But then we realized it looks a little too boring, so we make it a little more interesting. The details, the terminations, how the cranes would run on top. And finally coming to a structure that would sort of have details like this. This is a building that we'd done for Samundra's Institute. This was done a few years earlier, and it was the first large solar sort of installation more or less in Western India. The entire length of this building is 90 meters, and the entire south wall was completely made out of solar. The structure was, again, lightweight steel, Y-shaped columns, again 6 meters in one direction, 13 meters in the other. The building was sloping, so the north side was completely glass, south side was completely PV and BIVV panels. So it would sort of create a jali where you would get light into it. The other two sides were again glass, so lightweight structure, and creating bow trusses on one side to support it, and V trusses in the other direction. This is how it was complete. So we got a mix of BIPV and PV panels. in 2007, when it was completed, we could generate about 120 kilowatts of power through this wall. Today, we are going to revamp the wall, and we are going to get almost 600 kW of power from the same area. So you can see the efficiency that has changed in the solar panels per se. So these are the details done for the trusses at those times. Much smaller scale than that, about 8 meters height, 6 meters center to center, but basically no cross trussing. The bottom detail, the fixity, the movement, how the plates would sort of weld to each other, the gusset plates coming. It's all in the detail, and it's fun to create these details. And obviously then they are detailed out by the structural team, and they sort of detail it further, and then the fabricator comes with his set of drawings. And it's all a process that we as architects enjoy doing. And we can sort of build and experiment, create something different. It's still the same steel structure. And just, I think in the earlier, what we were listening to earlier, that how these buildings sort of, the old time industrial buildings were very rigid and very monotonous. But with the same concept, how they can be developed and created into something which is much more interesting, both visually as well as functionally. This is the cross section of the building when completed. Again, a very lightweight structure, completed in, I think, only 4 or 5 months after the erection started. So those are detailed drawings done. And the breakup, how the elements sort of merged into one another and created this lightweight structure. This is another structure that we done for a management institute. It was the dining hall come the multipurpose hall. The roof was, if you can see, it's in steel with a double pitch in it. This is how it is from inside. It's much wider than what it looks in the image. And it's about 13 meters wide with the hip into it, and the sky, double skylight on top. So again, it's a mix of two primary elements of construction, steel and concrete. Both of them are expressed in the pure form. Concrete as exposed concrete, steel as the way it is designed to be. So it's, again, it's a play of both light, shadow, scale. Dimensions are very important when we detail out these things. And we are very critical on how we sort of work out these dimensions along with the structural team. This was a bridge that was done in IIM Calcutta campus. It spans about 33 meters. It was called, the students there fondly call it Mini Howrah Bridge for them. It's designed for pedestrians. Unfortunately, 1 or 2 students decided to take cars across it. Nothing happened to the bridge or to the car. Both of them still survive. Again, it was an experiment of how to sort of create it, fabricate it, and then shift it over onto that. The sizes here are about 300, 330 mm dia pipes. Unfortunately, we had to import them at that time. Currently, they are available in India. And it was, again, the lightness of the structure and how the composite structure itself sort of develops itself into becoming both the element as well as visually strong. These are details of how the truss was fixed onto the concrete piers. Again, they may not be visually seen regularly, but every element has been detailed to the maximum. This is the pure mix of RCC and steel, the RCC pedestal and the steel being beam hitting into that. This is the cross section of the bridge. The actual walking area is much, it's a reduced area inside with both everything inbuilt into it. So the structure itself sort of lends stability to the overall. These are bridges we've done in IIT Hyderabad, linking 2 buildings. They are at different heights. Again, they work as composite elements, integrated both with the structure as well as in the RCC. So one side is hinged and one side is just resting. This was a workshop which we do a lot of work in COEP Pune. And this was one of the workshops that we got. Basically, they wanted it to redevelop it and make it into a G+2 structure. So this is how it was before. It was a stone structure from outside, load bearing. And we had to retain the external walls and rebuild the entire thing into a G+2 structure with this skylight come large examination hall on the top floor. And this is how it was before and after. This is completely revamped in steel. The existing exoskeleton sort of remains the same. It's a stone load-bearing wall. And inside we created steel columns, foundations, using a deck slab, and created 2 floors in it with this lightweight steel structure as the roof. This is another building that we were doing for Forbes, their corporate office. This was how it was before when we took it over, and then now how it was when it's completed. These are other buildings that we've sort of experimented with over time. Some are competitions, some are unbuilt, where we've used steel as both, as in its best, trying to create the play with different elements and getting the lightness of steel out. That was one of the main aims in this. Thank you.
This is about the footbridges, the footbridge, the tubular footbridge, and the linking corridors at IIT Hyderabad. What kind of movement joints did you provide?
Actually, that works more with the structural team. We as architects work out a system where one side is fixed and the other side is resting. So one side is fixed onto like how the anchor was shown. The other side, the bridge sort of just rests on a element. So there's an expansion joint on the other, both the sides, but one side is loose joint. It's not fixed.
I mean, if you are bolting it on one side, then you can have a movement joint only on the other side. You can't have it on both sides.
Could be. Means practically, I wouldn't be the right person to answer that. Thank you.
Thank you. Thank you so much.